you about inherently parallel methods design.
Okay, yeah, so many thanks for the introduction. It's a pleasure for me to be here. And I would like to talk a little bit about the Institute of Computational Science at the University of Lugano and about the work we are doing. Before I start with the scientific part, let me shortly comment on the Institute of Computational Science. As you might know, the Swiss Supercomputing Center, the SCS, is located in Lugano, which is a city in the Italian part of Switzerland, so in Ticino. And 3 years ago, the University of Lugano decided to put particular emphasis on computational science. So the Institute of Computational Science was founded in 2008. And the first one to go to Lugano in order to, let's say, start with building up this structure was me. So as a matter of fact, I arrived as director, and we are now, after being 2 professors in 2009, we are now 7 professors. We have created a professorship which is funded by Tianjin. We have some postdocs, PhDs, so the whole institute is about 55 people now, and as well. There's connected an educational offer in terms of master and bachelor to this new institution. And what goes parallel in time was an initiative in Switzerland called High Performance and Productivity Computing, or HP2C, which is basically HP2C, like performance and productivity. And within this initiative, we have been creating contact to other groups in Switzerland working in the area of high-performance computing and, of course, to the Swiss Supercomputing Center. So just to give you a short look, that's the colleagues working at the Institute of Computational Science, and down there you can somehow the building see where the institute is hosted. And as I said, that's a relatively new structure, but I'm very happy that we have reached a certain size, and of course I'm looking forward into future developments. We have tried to integrate the institute into the landscape of Switzerland and into the scientific landscape of Ticino, of course, and I very much hope that this meeting is, of course, fostering integration into worldwide partnerships. This is what I've been talking a little about. We have cooperations with local companies, we have created guest professorships, we have created cooperations with the other local educational institutions and research institutions, and we have created cooperations with other projects running in Switzerland. If you look at it from a more structural point of view, in terms of the HP2C initiative, the core group itself, which is designed to provide core functionality and core knowledge for high-performance computing in Switzerland, is located in Lugano, part at the Supercomputing Center and other part at the Institute of Computational Science. And as you can see there, we are working on extending our institutional cooperations. So much, let's say, concerning the organizational part. Now I would like to talk a little bit about science. We have been seeing talks today on ion channels, on molecular dynamics, and the first part of my talk is devoted to hybrid implementation of existing methods in parallel. And I would like to start with cardiac simulation. In particular, I would like to start with the simulation of the electrical activation of the human heart. Maybe you might know that your heart is beating because there's an electrical wave traveling around the heart. And wherever this wave is hitting a cell, the cell somehow contracts. And this is an interplay of a mechanical reaction of the cell and of a chemical reaction of the cell, which basically reacts to the activation potential on a very low scale by means of so-called ion channels. So the model basically I'm talking about in cardiac simulation is a multisphere model. Now this consists of a reaction diffusion equation basically for the activation front, and it consists of a microscale part which is taking care of the ion channels, which is modeled by ODBs. What we wanted to do basically was to get an established hard model for doing this reaction diffusion equation to a very good scalability, and we started with an established hard model which was created during the last year's party in Montreal by Mark Pozzi, who is now also at the Institute. And the idea is, what can you get in terms of strong scalability, and of course what can you get in terms of weak scalability. Strong scalability is of particular importance because at the end of such a simulation is always You are doing some simulation on the activation front, and in the end you would like to compute an ECG. And the doctors basically would like to run a lot of different runs with different parameters and different geometries, so they would like to understand what is going on. And so if you need a few minutes for doing such a simulation, it's fine. And if you need a few weeks, it's not fine. And just in order to give an order for the computation time, if you do it on a single core, you will have to wait a few weeks for the results. And of course, if you get good, strong scalability, you might do it in a few minutes. Okay, so what do we mean by a hard model? What we are doing is only the electrical activation part, so there's no coupling to mechanics. Geometry is stationary and mechanics is not in the game. This is a different thing, but we are just working on the electrical model. You have to account for the anatomy, of course. You have to take into account different cell types, which is done basically by material parameters and the ODEs attached to the different nodes of the finite difference discretization. And what you find here, the continuous system is basically a system of fibers going through your heart, which is transporting the initial impulse for the creation of the activation sequence. Sometimes the system is disturbed, and the activation front is not very well synchronized. So your heart does not beat good anymore, and the pump functionality is lost. And one possibility for doing a therapy here is to apply pacemaker, but then the question is where to put the different electrodes. And this question should be answered by doing this simulations. As I said, final goal is the computation of electrocardiograms, and as you might imagine, the activation front itself is very steep. So we have in space and time an activation front which has to be resolved very precisely, which requires a huge amount of unknowns. If you look at the model, it looks like this. So basically what you see in the very first part is somehow an heat equation. You see divergence of gradient, which is Laplacian, so you have global coupling in the model. This is simply diffusion of the activation front. Then you have first order derivative. This is basically the heat equation part, so evolution for the activation potential. And then you see E ion, which are the ion channels. This is the micro part, so to say, and this is basically ODEs. So you can think of these ODEs just as being attached to each cell of the discretization or each cell of the hearts, and these ODEs have to be solved separately. What is very nice about the ODEs is that they are completely decoupled. So the ODEs basically is where 80% of the computation time goes, but they are nicely embarrassingly parallel. What makes difficulties in terms of parallelization is the global part, which is given by the Laplacian, but this is as always, and here you of course rely on existing preconditions. I will comment on this a little bit later. The variable you are solving for are the membrane potential. There's an interior and an exterior potential. This is why this model is called the D-domain model. There's also a model which is called the monodomain model, which is a simplification, and where you have to solve only for one potential, and then there are some additional parameters which you know from measurements and from parameter studies, and this is how the domain looks like. I would like to mention the name ToM because the bi-domain model is used widely, but it goes back to one PhD thesis of 1978. But this PhD thesis is not often cited. So I just would like to cite it here and say the origin of the bi-domain model can be found in this thesis. You see it's on the bottom, but at least it exists on our side. This is how the heart looks like. What you see here in red is where the activation potential has high values. What you see in blue is where the activation potential has blue values, and you can see very well the strong gradients between the high and the low activation potential, and this is spreading over one heartbeat. One heartbeat takes about a second. So what we would like to do is to do a simulation of about 700, 800 milliseconds, close to a second, in order to do this computation of a human heartbeat. The discretization we are using in order to get efficiency is based on relatively simple data structures. So we are using a mesh which basically consists of voxels. So this is not an unstructured finite element mesh, this is a voxel mesh. And we are using finite differences because this is much more flexible, and as you know, for first order finite differences and finite elements on Cartesian meshes coincide only differences in terms of dealing with the boundary conditions. Okay, so what is the idea? We had a code available which was basically an OpenMP code, and we wanted to get scalability on larger machines. Let me just short comment on the time discretization. We are using IMAX, which is somehow a mixture between implicit time discretization for the global coupling part, which is Laplacian, and an explicit discretization for the ion channels, which are nonlinear, so we take the ion channels explicitly, and of course diffusion implicitly. So we have to solve a linear system per time step, but we get a good starting solution from the previous time step. So preconditioners, for example, like Bloch-Jacobi ILU, usually are reasonable, and then you get good scalability, and you get a little bit around of the stability condition for explicit order. In practice, what you see is that using this time of time discretization, you get a stable scheme even for larger time steps than could be predicted by the stability requirement for IMAX. What was our goal? Our goal was to get scale out and massive parallel clustered multi-core architecture. So at the SCS, there's a tray XE6. And our goal was to use a hybrid implementation, which is in this case MPI and OpenMP. We started from an existing OpenMP parallelization. And the idea then was simply to use shared memory or OpenMP parallelization for what is happening on the nodes, and to use MPI for everything which is happening between the nodes. We have to deal with our partly unstructured domain decomposition, because if you remember the geometry of the human arm, this is not a cube here, but this is a cube where somehow parts are missing. So you have to be careful in terms of load balancing and in terms of how to implement efficiently your linear algebra. Okay, so this is basically the setting, and now I would like to comment a little bit on the difficulties we had in working on this and on the advantages we could get out of our hybrid discretization. This is how it looks inside the tray 65 system. So in each node you have two 6-core NMDs octons, which are connected to the respective RAM, and then of course you have the interconnect by a C-star interconnect, and the idea is simply to use local, the OpenMP part, and to go globally for the MPI communication. And I would like to discuss a little bit in more detail what the benefits of this approach are. And in order to do so, let me consider models for the human heart of different size. So we have small, medium, large, and extra large, and the resolution you see here is actually in space. So this is between 3 million nodes, which is the small model, which is a resolution of 0.5 millimeter, and extra large, which is a resolution of 0.0625 millimeter, which corresponds to 1.6 billion degrees of freedom. To our knowledge, that's the largest heart model ever computed, which is of course going to change soon. But these are somehow the different models we are considering. To go for a much larger model does not really pay off, because you here are on a scale where you resolve the anatomy and where you resolve what is happening on the ion channel level, on the cellular level, already with a very high accuracy. So going for a larger resolution is not good, so you have to look in particular at strong scalability. Because weak scalability simply would mean increasing the size of your problem, which is nice, but the doctors say already this is too fine because it contains too much information. Okay, so how does scalability look like? What you see here is scalability runs, and you see the different colors for different number of threads per processor. Right? You can go for a pure MPI implementation where all the communication between the different processes is done on an MPI basis. Or you can go for 6 or on the XT5 up to 12 threads per processor, which is the green line, where you have different number of threads and less communication inside MPI. The advantage you get here is less, so to say, due to the fact that you don't use MPI. The advantage in terms of speed up is basically due to the fact that the hybrid model, where you use shared memory and MPI, simply creates less number of unknowns. Yeah, whenever you have a domain decomposition and you split your domain, you have to increase the number of unknowns, and you have to create some ghost unknowns because you have to double the unknowns at the interface. If you do it in a shared memory context, you don't have to do this. Yeah, so you get simply less to do because you are using locally OpenMP or shared memory parallelization, and this is what you can see for the green line. So on the left-hand side, you see for the simplified monodomain model explicit Euler. On the right-hand side, you see IMAX Euler. And you see there's a considerable advantage of doing it with the hybrid variant. Also, at a certain size, of course, strong scalability breaks down simply because you don't have enough unknowns per core anymore, and communication time then is dominating somehow the complete runtime. If you look at the increase of degrees of freedom per century, and this is the last table you can see down here, for the different number of threads per core, and here we had 1, 6, and 12 threads, you see that the hybrid implementation uses only, or gives rise to only like 11.3, this is lower right corner, percent of increase of degrees of freedom, whereas if you go for a pure MPI implementation, of course you get like 30% overhead, which is basically reducing your efficiency. In this case, you go up by means of the hybrid implementation from like 78 to 89%. Yeah, which is, I would say, for the number of degrees of freedom we are handling here, quite a good way. So in the end, we can do a reasonable run in like 5 minutes, and this is what is useful for good parameter schemes. Currently, we are of course improving performance, in particular with respect to I/O. For example, in each time step, we do not write a complete solution. The solution is a little bit compressed, so to say, before we write it out, in order just to reduce I/O. And yes, we have a trace project running where we would like also to improve this kind of implementation. It might be an idea to accelerate this by GPUs. We haven't done this yet, but the easiest way to do this would be simply to take the ion channels and to put them on GPUs, because this is something you can extract very nicely, and this is where most of the computation time goes. And of course, I have to comment on the bi-domain solver. What we also tried was using algebraic multibit like Boomer, but it scales up to like 1,000, 2,000 cores. But if you go for larger problems, some more scalability of algebraic multibit breaks down a little bit. You get a large memory overhead, and this is why we are using something like a block edu, which is sufficient because we have a good starting solution from the previous time step. Okay, so this is what I would say is somehow a classical approach, and to get performance and scalability. And now I would like to come a little bit closer to the core idea of my talk today. If you look at the title I wrote, it's from parallelized to parallel. My argument is very simple. What we do in high-performance computing very often is we take existing methods and we parallelize them. And then we're looking for efficiency, scalability, weak scalability, strong scalability, and high number of costs. But you also, of course, have the possibility to create algorithms which are parallel by design and which might differ from a parallelized serial algorithm. And in the later part of my talk, I would like to give 2 examples for this idea. The second part I would like to comment on, which, because this is, again, in terms of, let's say, classical methods and high performance, is fluid dynamics. If you take Navier-Stokes and write it in vorticity-velocity form, you get this equation you can see here. And then you can say this is a very special formulation of the incompressible Navier-Stokes equations. Why is it interesting? And the argument is the following. You can use it in order to derive a discretization which in the end is leading to a particle method. Right? You can exploit some relations from vector analysis, you know. You can use Wien's function because you have Laplacian inside for the pressure. And then you can discretize the vorticity field with so-called regularized particles. And basically you see the particles in the sum, and you have some kernel functions which are these zeta sigma, which basically define the size of the particle and the smoothness of a particle. So you attach somehow to points basically where you put the particles a local weight function which is giving you the influence of this weight function on the global vorticity you compute. If you apply then the discretization to U, you obtain the discrete representation you find in the last line, and this is the basis for our particle method. What you have here, of course, is global coupling. And let me just comment shortly on the particles. This is what we are using. We are using algebraic smoothing kernels, which are defined like here. This goes back to the PhD thesis of Robert Speck, who made PhD thesis in Jülich and in Wuppertal. And this is a little bit in contrast to what you can find in other codes because the Gaussian kernels are used. But we decided algebraic kernels are worth trying, and as we have tested out recently, it's also a very good idea. In principle, what you get is long-range interactions. So you have interactions basically like 1 over r, and in order to get rid of the n square evaluation between the particles you would have to use them, we are using here multiple expressions. Okay, so let me just shortly comment on how this works. In principle, as I said, each particle should interact with every other particle, and the exact calculation is often not necessary. Yeah, we had this in the talk about molecular dynamics. As far as I understood, the potential use was somehow also using global interactions, so there should also be some kind of multipole expansion inside. So what you say basically is you cluster distant particles, and the interaction of particles with distant particles are simply replaced by interaction of particles with distant clusters. And so you can reduce the n-square operations to n log n. And of course you have to have efficient data structures which are able to handle this. The idea is here to use a Barnes-Hart tree code. So you have the particles, as you can see here. Then you take a space-filling curve, in this case in 3D, which allows for ordering the particles in the way you can see, and then of course for very easy and efficient load balancing, because after attaching the particles to your space-filling curve, it's only one-dimensional, you just have to divide by the number of processes and you get a good load balancing. Then what you do is you create a tree, as you can see on the right-hand side, adaptively, until basically in each of the leaves you have only one particle remaining. This is what you see over there. And once you have done this, you can create the global clustering. You see here again the decomposition of the different processors, which is coming from the space-filling curve. So from the particles over space-filling curve and tree, you end up with the decomposition you see on the right-hand side. And then you do what I said before, yeah? You just replace some of the interactions of single particles with the clusters, and so you get the efficiency of the multiple expansion. You have to do a tree traversal in order to implement this, and we have implementing, or Robert has implemented basically this kind of Navier-Stokes solver in the framework of a larger code family, which is called PEPSI, which is pretty efficient parallel Coulomb solver, which has been developed in Jülich, and here you can see a sketch somehow of the structure of this code. And we have been using this in order to create a vortex tree code, which is part and spin-off of the PEPSI library. And what are the advantages, or what are the basic points behind this? It's completely mesh-free, and it's massively parallel. I have to say that after some time steps, of course, you have to do some remeshing, and you have to do some interpolations in order to get values to new particles. But besides this interpolation mesh, which is a Cartesian one, the code is completely mesh-free. We have multiple expansions up to quadruple moments because we're using the algebraic kernels. And we have the generalized algebraic smoothing kernels, which turned out to work very nicely. Now, in terms of scalability, let us consider these standard examples, which are basically totally moving in space and interacting with each other. So you see a time snapshot of a time-dependent parallel simulation. And you see here increasing number of particles, 10 to the power of 6, and then up to 10 to the power of 7. What we did, and this is interesting in terms of scalability, we have very good scalability, so we have used the full Eugene in Jülich, which is 296,000 cores, I believe, and we made up to 2 billion particles, which is possible because we have a very sophisticated inter-node load balancing, yeah, otherwise you won't never get this good scalability. And we have tried to be open for upcoming architectures, in particular also for what is going to happen at the SCS, because the SCS in Switzerland is usually run on a credit basis. Okay, now let's have a look at the scalability numbers. This is what you get. And if you see, as usual, breakdown of strong scalability, but depending, of course, on problem size. And here, of course, the larger the problem is, the better the scalability is. So from my point of view, this is very good scalability. And as I said, we have 2 billion particles on the full Eugene, which is a step forward for extraordinary big machines going to come. If you look at this, this is somehow an established method which is again implemented in a very clever way, and where you have to use a lot of tricks and ideas in order to get it up and running and scaling, which is always the case. Yeah? If you don't use the reasonable tricks, you won't get scalability, but we get best scalability for well-established standard methods, and there's a slight change of paradigm, because what we are doing in order to evaluate methods, usually in numerical analysis, is just we count the number of floating point operations, yeah, which is not sufficient anymore because you have to take communications between the different cores into account. And so the question is there better measures somehow for overall complexity, like overall computing time, something, for example? And what is also very crucial for these kind of methods is that you have an extremely good load balancing. Now, as you know, computing the load balancing itself, right, is NP-hard. So if you go for a very large problem, it might be that computing the load balancing already is a challenge. So the question is, might it be possible to design new methods which turn what was sequentially up to now, or what was done in a very synchronous way, into something parallel and asynchronous, and this is what I would like to comment on shortly now. The first idea, or the first what I would like to discuss is parallel and time integration. Maybe you have heard about parallel. As you know, time integration, as we learned at university, is completely sequential. Yeah? You start from an initial value, and then time step per time step you compute your evolution. So that's a process where you can say this cannot be parallelized. Parallel is now saying the following. Assume just at different time steps, which are called capital T, you have some start solution available. Then you can compute in parallel somehow on these time sub-intervals the solution, which then at the end, of course, at the interface is not going to match. And what you do is now, in order to get these starting values, you use a very, very cheap, computationally cheap coarse integrator, which provides you somehow the star values, and then you use the computationally expensive but accurate fine integrator, which is somehow giving more accurate information on the sub-intervals. Yeah? So this is how it looks like. You get starting values by using the G, which is the coarse predictor, and then you refine. And as you see, the trajectory is not continuous, so what do you have to do? You simply have to iterate. And as you do, this imposes some partly sequentiality in your code, which is basically coming from the coarse predictor, but it allows you to do a parallel space-time discretization. So if you like, you can see this as a multi-grid method in space-time, or as some kind of multiple shooting method. And I would just like to show the effects of this for a full Navier-Stokes simulation needed. So what is the argument? Again, we are using a hybrid discretization with MPI and OPMP, and we are considering an Navier-Stokes code which has partly been developed at the University of Bonn, and which is basically state-of-the-art with a stabilized, or with TDP update schemes, and this stabilized basically stuff for the pressure correction. This is mostly standard in fluid dynamics, but what is not standard is the combination with parallel, and I would like to show you the results. Because what you say is basically you take your discretization in space, and then you distribute in space until somehow scalability breaks down. Right? So you have less unknowns per core, scalability breaks down, and then you say, this is the point where then I start to use parallel computation in time. So when scalability breaks down in space, you go to scalability in time. And we did the experiment you can see on the largest machine, which is available at the SES up to now, which is Monte Rosa. And here you see some technical data of Monte Rosa, which is going to change soon. I mean, as you know, computers are replaced on a regular basis, and CSCS recently got a new building, so I'm sure there's new ideas on what is going to happen. Okay, so our test example basically is driven cavity. There you find some technical details on what is going on. And we have a space decomposition, in this case up to 256 processors, and we are trying to look at the gain you can get if you do integration parallel in time. And this is the results. What you see basically is the saturation of the scalability in space if you increase the number of processors, yeah? So there is no gain. But what you can see also is if you use more processors for the parallelization in time, you can shift this threshold a little bit, and you can get better scalability just by adding time parallelism. This is nice. I have to say parallel is not scaling as good as usual spatial problems, yeah, because the algorithm itself has some sequential parts, so you know the scalability of parallel is bounded, but once you don't get scalability in space anymore, you can improve still by simply adding parallel. So this is something you can add to your code, and then you can get a factor of 5 or 10 or 15, whatsoever, more or less for free, in order to go to larger machines. I'm convinced there's going to be new developments in this area, but we're happy that, let's say, this possibility at least can be exploited and is useful for this kind of problems. The last problem class and method class I would like to comment shortly on is just nonlinear mechanics. So here you see a cube, which due to the application of outer forces is deformed. And if you look in mechanics, usually you describe this as a kind of minimization problem. So you have potential energy or elastic energy of your body, which has to be minimized, subject to some constraints, maybe non-penetration constraints like in contact problems. The functional is non-convex usually, so you have to be careful in minimizing. You will not get a unique minimizer, but this is how it usually works. There's a very well-established strategy for this, which is trust region. And what you do is you take your nonlinear functional J or your non-convex functional J, you approximate it locally by a convex or quadratic functional, which in this case is called psi, and then you restrict the validity of your local approximating model to a trust region model. And then you have a control criterion which tells you if you reduce your energy sufficiently, you are allowed to increase the trust region radius because your model was good, and if not, you decrease it, and so you can show global convergence at least to some minimizer. This is how it looks technically, but our argument is the following. If you consider a nonlinear problem, like the one sketched here, it might be that nonlinearity is highly local. Yeah? So what can you do? You can say, okay, instead of taking the global nonlinear problem and linearizing it, I just solve a sequence of local nonlinear problems asynchronously and independently. And this basically looks like this. You have a large-scale nonlinear problem. You divide it into several small nonlinear problems. You have a recombination step, which is including convergence control, and so you iterate in the local nonlinear problems. You can solve asynchronously and iteratively independently from each other. And if you have the right recombination strategy, you will end up nicely. You can do this on a multi-scale level, and let me just end up with this slide here. This is what we get. What you see in the left sketch basically is reduction of energy. It's a monotone algorithm, so energy should always be reduced. And what you see on the right one is reduction of the first order necessary condition, which is known as a gradient. And the steep descent is just close to the solution. You are acting like Newton's method, so you get quadratic convergence. And the interesting thing here is also the theory does not tell you anything about convergence speed, independent of the number of cores we have been using for this implicitly or inherently nonlinear method. We get very similar decrease of first order necessary conditions. Yeah? This is very nice. Cannot be predicted by theory because you are solving independent nonlinear problems, but you see the algorithm somehow behaves nicely. Okay, so and with this is what we are doing at the institutes in terms of areas. Many thanks for your attention.
Questions?
Thank you. Okay, so we are coming to our last speaker for the panel, Professor Chen. He will speak about computational fluid dynamics.
So I'm asked to talk about the applications. Since we have quite a few computer scientists here, so I take the liberty to expand a bit on the computer science aspect. So I'm from Peking University. So this is a collaborative work with our engineers. So I'm from informatics or computer science. We have an engineering department as well as NUDT and our Tianjin Center. So this is a collaborative thing. So this is a summary of our work. So in terms of, this is a direct simulation of turbulent flows. The scale is up to 14K 3D single precision. It's like a 12 distributed arrays add up to 128 terabytes. So we used the entire Tanker machine, including the GPUs. So the performance of the turbulence simulation is highly dependent on FFT's performance. So we have a GPU version of large-scale FFT earlier on published at SCS. So in terms of progress, the current world record is 4K 3D. So we are halfway into 8K, but only tested for 14K 3D because it obviously uses a lot of computing resources. And along the way, so we developed a number of software technologies, including a programming interface. It's called P-Array. We also published it recently at P-Pop. And also we developed some resilience technology, means some small software tools to enable you to maintain a stable computation with very big scale of simulation. So the entire conclusion, so the first one. So it's actually GPU accelerated large simulation on the entire Tianjin machine is actually feasible. So for heterogeneous parallelism, we get many processors, many kinds of threads, many types of memory, and many different patterns of communication. So this is the source of complexity. So let me give you a motivating example for our software technology. Let's say there is one computing node with 2 GPUs. Okay. So here is a network. Let's say, suppose we transfer a 4K by 4K array to the 2 GPUs, but we divided it by 2 partitions first, the 4K by 2K. So each going to a different GPU. So what's the best strategy? That is to transfer the 2 array blocks in parallel. Right? You use 2 CPU threads controlling the GPUs, then transfer in parallel. When you do that, you get an overall bandwidth like 60% better than you do it sequentially. So this is a sort of parallel host-to-device transfer. But of course, you can do something similar, but quite different in some other aspects. So this is a network of 2 computing nodes. So you get an array here in one node, 4K by 4K. So you scatter it to 2 nodes, right? What you do is you get a 4K by 2K in one node and another node. But look at these 2 different communication patterns. They do have different devices across different network communication media. But they do share the same communication pattern, logically. Okay. So this is the motivation. We want to capture some of these uniform characteristics across multiple, manifold, as well as clustering parallelism. So, I give you some very basic notation. If you learn this slide, that's all about P-array as a programming interface. So you write an array like this. So you get a float, like C notation. But slightly different is that you get a nested kind of a dimension trees. So you get a 3, 4, 2, 4. There are slices of the dimensions. But 3 and 2 form a dimension as well, which is like a sub-dimensions. So this hierarchical structure actually reflects the hierarchical nature of the memory, because we get a heterogeneous memory structure. So, and also you indicate what kind of memory you are going to create this array into. So you get a DMEM, the pin is actually in the main memory, but it's DME very fast. And DMEM is actually in the device memory. Okay. And another feature of this notation is that you refer from one array to another array type. So here in this particular array type, you actually swap the 2 dimensions. Then you use these notations, just these 2 simple notations. You can play a lot of interesting things and get very succinct program. So go back to the original example. So in P-array, we have actually arrays containing threads, processes. So say for example, this is like a P threads, so the CPU threads, 2 CPU threads. That's an array. You can get 2 MPI processes, so they are treated uniformly. Also CUDA, this is a CUDA a program with many threads. So the original motivating example is now actually a communication pattern from main memory array memory to a distributed array. This particular array is distributed over multiple processes, as well as the device memories. So it's actually scattering main memory data to different devices. Then the similar pattern is actually, you can describe MPI scatter. So using this program notation, we have a source-to-source code generation. So this is the code actually you write for this particular data transfer, parallel data transfer to multiple GPUs. So you see, you declare in this particular code, you first declare some array notations. They are added to C. So this is interweaved with C. So C can call P array can call C. This is the main code. In the main code, you're actually generating two CPU threads. In each thread, you initialize GPU, one GPU, and create an array, and do the transfer. So the whole program actually does this parallel transfers to two GPUs. You can imagine how you write it using CUDA, as well as P array. P threads or OpenMP, whichever you like. And for the similar pattern, you can write this example. This is an MPI scatter. If you want to try scattering, then you change the threads to the nature of the thread from P threads to MPI. You change some types. The red things are updated, changed from the previous code. So this code is doing similar thing, but across the communication network. So you write two very similar programs, but they are compiled to generate very different codes. One dealing with handling CUDA, the other using MPI, because they are in nature, they are similar programs. So when the programmers see them similar, it's just the implementation and the hardware you use is different. And also you can describe many different kinds of communication patterns. In fact, there is a certain completeness. Whenever you are able to write an index expression, you can use the notation. So here, for example, you can have an auto described in that way. Broadcast or grouped auto. So you have 100 processes, but 10 in each group. Then you do auto inside each group. Or you actually can do this sort of permutated group-wise auto communication. That's group I communicating with another group J, but actually it's an auto between I and J groups. So you can write these patterns, no matter it's across the network or across PCI. Similar thing, it's just a type difference. You write them into the type information. So this is the large-scale FFT, only 30 lines of code. The original code published in 2010 at ICS was actually 300 or 400 lines of code. That code was low level, which is CUDA, pthread, MPI, low level code. It's fixed for a particular smaller cluster. But this code, it maintains the same level of optimization. When you write the code in this way, you don't lose the level of optimization. So you still have the control over system level features, but you control them in a nicer way. Instead of you writing very low level assembly line like code, you still control them. This is what I want to emphasize. So using P array, you still control system level features. That makes sure that you can achieve the best performance. So it's like a performance transparent layer of software or programming. So this 30 lines of code is not easy to write. It's difficult because intellectually it requires the same level of intellectual challenge to devise the algorithm. This particular algorithm published at ICS was actually to provide a chance that you don't use main memory operation at all. Because in FFT, you need a global transposition, which involves main memory to main memory operation. But this algorithm doesn't do that because you have GPUs. The existence of the GPUs actually make sure that if you do some clever kind of dimensional manipulation, you don't need that main memory operation. Okay, anyway, so the same level of optimization, you can use a more abstract programming interface to write it very short. So it's easier to make sure you write it. It's easier, I can't say it's easier, it's a sort of a nicer way to write 30-line code than 300. Also, because we want to do this real application turbulence, it involves many arrays of FFTs. So you need a resilience technology. Well, if we go to XR scale, no matter you use traditional cluster or GPU cluster, you inevitably you have to apply resilience technology. So we use several months on the Tianjin because we work with the whole machine. So we developed some software tools that allow you to, when you use P-array, the software tools would allow you to actually handle connectivity problem, single GPU problem, as well as memory problem. Okay, so this is the way you actually use a bigger pool of computing nodes. In effect, you use only a small, not small, a subset, a big subset of it, and you don't use the faulty ones. Some nodes, they are not entirely bad, but they are flawed for a particular application. They're probably perfect for another application. So this is a sort of semi-healthy nodes. You have to exclude them in your application. This is the technology we developed along the application months. So this is the code you actually can exclude nodes. And also you exclude those slow things, slow parts of the machine. So this is the FFT's performance. Actually, we get it better now. This is the old last year's. Compared to MKL, it's faster, also more scalable, because you get a GPU which avoids main memory operation. So before K, last year, we are actually on the FFT benchmark, we are first. Without GPU, this is the without GPU benchmark using MKL. Intel MKL, CMKL is a cluster version of MKL. It's actually very optimized, but it doesn't use GPUs. So if you use that, the whole Tianjin machine is actually slower than the comparable Jaguar. This is a smaller problem size, it's easier. So this is more comparable. But if you use GPU and a new algorithm, you get a much better performance. So this is the turbulent flow simulation. I can't answer questions about this figure because this is our collaborators' domain field. So anyway, this number is sort of illustrative. So we have halfway into 8K cubic. And this is the performance. We have about 30 teraflops because this is a communication intensive application. So we get a lower floating point speed. Okay, I added one slide. I thought I should omit, but actually this is more interesting to this. What is it? So I mentioned that P-array is sort of, you get very clear type. So you handle system level features in a particular way. One thing you can handle, use this idea is to put into some like HMPP. So if you have a dual type, so this, because in HMPP you can update a variable which is defined for both main memory and device memory, right? So you can like update then is copied. But you actually can write two types, one array type for its form in the main memory, and another type B is the target type in the device memory. Okay? So if you write things like that, what you can do is that you don't change the original code because HMPP assumes sequential code unchanged. But what you do is you change the layout of the data when you transfer it from main memory to the device memory. Okay? Then in the device memory, it becomes coalescingly efficient because the GPU is very sensitive to the layout of memory, layout of data in the device memory. So you can play this game. Also, but of course, you think this is manually written. You have to intellectually figure out what's the target type, how you write these types. I wouldn't say, but you don't change the code. But in the future, as Caps already showed us, it's possible, I believe it's possible to auto-tune this. So these types, we could theoretically generate, in principle, generate different types automatically. And you have a performance model, then you can try what's the best for the memory coalescing, to make it memory coalesce. So represent things clearly first, then think about optimization. That's the lesson we learned from this the work. Okay. So in summary, so we believe Tianjin is usable for computation over the entire system, including GPUs. But you must employ the latest software technology. Without that, you will get trouble. Even something you think is strange, but that's because you are not using the latest technology. We have programming. So I'm a programming language person. I studied programming theory. The main thing for me is to make sure people learn our tool, our programming interface. So we conducted some training course. I was inexperienced, but we managed to make sure people understand it on the third day. I hope that I can do it better next time I do this. So they really understand it, because when I make mistakes on the whiteboard, they were, okay, you are making too many mistakes. Anyway, also I think my experience is that the notation is actually friendly to computational engineers and also geophysicists and so on. Not particularly for computer people, because computer people sometimes like pointers, programmer coders. But the computational engineers I met, they like matrix notation, in their books. They are so happy with matrices. So this is kind of an algebraic notation. It's actually friendly to them. So, but actually they are the target users of this particular tool. That ends my talk. Thank you.
Questions?
Your training course is giving here in Tianjin?
No, I trained it in Beida, Peking University. But so we invited financial people, and also oil industry, as well as from Eastern. Also, some people, various kinds of application areas. I think it's like 40 people from different applications. So they pick up on 30, which was surprising to me. Yeah. Also, physics, astrophysics from Peking University. They are doing like a black hole simulation things as well.
More questions? I have actually one. So I can see the advantage of using this notation if you have a dense matrix problem. But there's many applications that use sparse matrices.
Yeah.
So what do you do here?
Yeah. So one application I'm looking into already did some work is oil reservoir simulation. In these kind of applications, it's often a mixture between regularity and irregularity. So the physical model is actually three-dimensional mesh coming out of the finite difference computation. You do the sparse solver, solving the sparse matrix. So the sparse matrix is actually not ad hoc in time. It has a certain mesh into it, structure into it. And the best algorithm is always to utilize that underlying structure. So I think PRA is like something you do, it does something for you, except what it says on the tin. So it doesn't stop you to employ other tools that handle the irregularity. So I think for the irregular part of the problem, then you can encode it into the arrays. That's actually the application developers always do. So they have to, if they want good performance, they have to utilize the regularity. But of course, if your problem has a certain aspect which is irregular, so you probably can employ some domain-specific languages. Could be helpful. Yeah.
So thank you again very much. Thank you for this interesting talk. And now over to you. This is the panel director chair.
Okay, we'll do that. Okay, and
what happens next time? So we have a panel discussion.
This is highlighting.
Yeah, panel discussion. So all the people are at the table, you are members. Facilitators. Communication, right? It's simple, it's